Hey everyone, today in this video I'm going to be introducing contrastive learning, which is a super important part of deep learning that we will see come up over and over again when we get to the portion of the course about economic applications. So at the core of many deep learning applications is a simple idea that we want the representation of instances belonging to the same class, regardless of noise or interclass variation, to be similar, and representations of instances belonging to different classes to be different. And so this could be in a context like OCR. You have lots of different fonts and handwritings and ways to write a letter A, but you wanted to always have a similar representation. This could be in the context of NLP, representing similar topics with a similar document representation. And so this concept relates closely to Siamese networks, which are designed to learn the same representation for instances from the same class. And contrastive learning is a subtype of Siamese learning that learns from negative samples as well as positive samples. So positive meaning they're from the same class, negative meaning from different classes. All right. So I'm going to start out by introducing contrastive loss functions, and then I'll spend much of the lecture talking about self-supervised contrastive learning and vision, which was an area where contrastive learning really took off. But I'll also mention briefly supervised contrastive learning, semi-supervised learning, and contrastive learning in the context of language. As I said before, when we get to applications, we'll see contrastive learning come up over and over again. Those are mostly going to be in supervised settings, but I think understanding its evolution in semi-supervised and self-supervised applications is important for understanding this literature, and so that's actually what the bulk of this lecture will focus on. All right, so the general idea behind contrastive loss is that we want embeddings of two images or text or other samples to be closer together if they're from the same class, broadly speaking. And that's going to be what a class means is going to be defined based on your application. And we want to pull them apart if they are not from the same class. And so we need some loss function that penalizes the model if either of these are not the case. So we want to penalize the model if objects from the same class, if vector representations of instances from the same class are not nearby. And we also want to punish it if the representations of instances from different classes are close together. And there's been multiple loss functions that have been used to do this. The best function is going to depend on your particular application and on the available data. And again, we'll see this developed in more depth when we go into the applications portion of the course. And so one type of contrastive loss is cosine loss, where the data are pairs of instances and a continuous label of the distance between them. And so if you have a context where there's some sense in which instances are similar or dissimilar in a continuous way, this is what you would use. Contrastive loss. So in this case, we have a list of samples, and they each have a corresponding label where the labels are C classes. And so that might be, I mentioned doing OCR, what character is this? But it could also be a variety of things. And you don't have to have enumerated all the C classes. Like your labels might be these are the same or these are different. So f theta is the function that converts xi into embedding. And we take a pair of inputs, xi and xj, and minimize the embedding distance when they're from the same class, but maximize the distance otherwise. And here, epsilon is a hyperparameter, and it defines the lower bound distance between samples of different classes. Triplet loss. So imagine you have data where you have an anchor example, and you have one positive sample and one negative sample. And In the context of triplet loss, you're learning to minimize the distance between the anchor and the positive sample and maximize the distance between the anchor and the negative sample. And you're learning to do that at the same time. Where, again, you have this margin parameter that's configured to be the minimum offset between distances of positive pairs versus negative pairs. And that's a hyperparameter that you'll need to choose. Okay. Another common function is called supervised contrastive loss. And what supervised contrastive loss does is to allow for multiple positive pairs in batch. So given a set of in-image labeled pairs, you can use data augmentation to create 2 random augmentations for every sample. You don't have to use data augmentations with SupCon, but that's the way it was presented in the original paper. And now essentially, you're able to have multiple positive pairs in your batch. And so kind of if you're new to contrastive learning, you might say, well, why is this a relatively recent paper? The SupCon paper came from 2021. Why did people do these other forms of contrastive learning beforehand? And the answer to that question and to the name, why this is called supervised contrastive loss, is that traditionally with contrastive loss, it was used in self-supervised settings. And you would use data augmentation to get your positive. And you just have one data augmentation that you do, and then the rest of the batch was negatives. But if you have supervised data, clearly you might have multiple positive examples for a given anchor. And SupCon is essentially a generalization of the info and CE loss that allows you to have multiple positive pairs in batch. All right, so this is an intuition for SupCon. So here you see that you have an anchor, and on the left-hand side, you're doing self-supervised contrastive learning. So you have a random crop of that anchor, and that's your positive, and then everything else is your negative. Whereas on the right, you're doing a supervised contrastive loss. So you might still do that data augmentation from your anchor, but then you also have another picture of a dog here that then becomes part of that same class. Whereas if you don't have labels, then obviously you don't know whether things in your unlabeled data kind of may be part of the same, specifically defined class. Instead, in self-supervised settings, what it means to be positive is just to be a data augmentation of the anchor. Okay, so we'll talk about these kind of a little bit more as we go along. And so I want to start by talking about self-supervised contrastive learning in the context of vision. So much of the contrastive learning literature developed around self-supervised training for computer vision, and understanding that is helpful when you're trying to navigate this literature. So in self-supervised settings, data augmentation is very much at the heart of contrastive learning. As we just saw with SupCon, it may be used in supervised settings as well, but when you're in a self-supervised setting, data augmentation is how you get a positive sample to learn from in contrastive learning. So data augmentation introduces variations into your examples without varying their meaning, their semantic meaning, and hence encourages the model to learn the essential parts of the instance for the representation. Getting the data augmentation right is important. If you're in the state of the world that we were talking about in class, where your model isn't doing what you expected, it's not behaving well, and you're doing some data augmentation, that might be a first thing to check that it's going correctly, that you're doing it correctly. So there's kind of standard types of data augmentation that are applied in vision application. So random cropping is particularly central, having different views of the same image. Random color distortions, random Gaussian blur, random color jittering, random flipping, random grayscale conversion, and other similar augmentations. All right. So I want to introduce an architecture called SimCLR that was used for self-supervised learning of vision models. And so you start with some instance X, and you're going to take two augmentations of that. So that could be two different views of the same larger image. We can call those XI and XJ. And then you're going to pass both of those through an encoder. So in SimCLR, I believe this is through a ResNet. And then you're going to have an MLP layer that projects those representations down into a lower dimension. And you're going to compute your contrastive loss over those lower dimensional vectors. You don't have to project into a lower dimension to calculate your contrastive loss, but this paper argued that that worked better, and it popularized that approach. And so it learns visual representation by maximizing agreement between the differently augmented views of the same sample using a contrastive loss. And so specifically, you sample a mini batch of n random instances, and 2 data augmentations are applied to each instance, resulting in 2 n augmented samples. Given one positive pair, the other 2 n-1 instances are treated as negative samples, and the representation is computed using this F function, i.e. a ResNet, and then you project that down to lower dimensional representations. And contrastive loss is defined using cosine similarity. The loss operates on this extra projection layer, as I mentioned. And so you can see that this is essentially a loss that's very similar to the SupCon loss, but now you only have one positive in your batch because you got your positive relative to your anchor by doing data augmentation. And so just to go back and to review this architecture, so you have this F function on both sides, and this is symmetric. You have the same function on both sides, and you have you're passing through these different views of the same underlying image, and you want to maximize their agreement. Whereas if it's the negative pairs in the batch, you want them to be maximize their difference. And you do this by using the following loss function, which is really very intuitive. Tau is just a normalization parameter that controls how peaky the loss will be. And so you want to maximize the similarity in the numerator and minimize it and do the opposite in the denominator. And so that your negative samples are as dissimilar as possible. And so the problem with this, and we'll see this in more detail in a minute, is that the model needs to see enough hard negatives in batch to achieve good performance. Because a lot of the randomly sampled negatives in your batch, they're just going to be very different. And kind of the pre-trained encoder will already know that they're very different, so you just don't kind of learn too much from those samples. And so when you see kind of these very different samples, the model just doesn't update a lot because it quickly learns that that these are different images. So you really need harder examples to learn from. Examples where two different images, like the representations of two different images, are nearby, even though they shouldn't be. So if you're working in a supervised setting, you might explicitly create hard negative pairs based on your knowledge of the problem. And we'll see examples of this throughout the course when we get to applications. And oftentimes that's kind of a best case scenario. But obviously, if you're in a self-supervised setting, you won't know explicitly necessarily based on kind of external information what is a hard negative. And so how do we have enough information for the model to learn? The naive solution 1, which is what the SimCLR did, is just to use very large batches, because in a self-supervised setting, negatives grow quadratically with the size of the batch. But the problem is that this is not a realistic solution due to the high cost of GPU memory. And so kind of in reality, to get large enough batches that these models would perform well just by having informative enough negatives through the M-batch examples, it takes compute like on the scale of something you might have access to at Google or whatever, but certainly not in the vast majority of settings. The second naive solution would be to compute the features of each instance in the full training set at each iteration and use that to sample hard negative pairs. And so you'd sample for the batch the vectors that are closest to your anchor. And that obviously does not work either because it is extremely time consuming for large data sets. You have a huge data set and you would have to pass each instance through this high dimensional encoder at each iteration of the model. And so that's going to be completely impractical as well. And so this led to ideas about how we can kind of get around the need to have such a large batch size. And what if instead of having a large batch size, we had a constantly updated queue of recent batch encodings instead? And so this idea was developed by he et al. Again, Kaimin He, we'll see him over and over in vision applications. And they developed a model called MoCo with two encoders. So it had a query encoder for incoming online data and a key encoder for maintaining a queue-based dictionary of recent batch embeddings. And this queue cycles new batches in and old batches out at each training step. And this enables using the queue of past embeddings as a pseudo batch of negative pairs. And so we do not use backprop to update the key encoder. Instead, they used what's called a momentum encoder, where you update it as a weighted sum of the key encoder and the query encoder, where here M is momentum and theta k are the parameters of the key encoder and theta q are the parameters of the query encoder. And so this is essentially an exponential moving average of the query encoder parameters, and M is set very high. They set it to 0.999. So if this sounds familiar, it's because we saw this with Dino when we were talking about VITs. And so in the case of MoCo, which is a 2019 paper, the query encoder is a ResNet, and the query encoder minimizes the influence-CE loss by minimizing the difference between the query and key embedding for the single positive pair, which is created through augmentation, and maximizing the difference for the negative pairs. And so again, this is the same contrastive loss that we've seen before, and the dot product between the embeddings is the similarity score. Okay, so this is showing the model graphically. So you have this query encoder, which is a ResNet, and you're getting representations from that. And then you have the momentum encoder, which at each iteration of the model, you encode some new keys, and then you remove the oldest keys from the dictionary to make space for these new keys. So it's like a dynamic dictionary. And then to get your single positive pair, you have that at each step. And then to get your negative pairs, you're looking them up in this dynamic dictionary. So you might be taking representations from previous iterations of the model, but since you're kind of cycling them out and it's this dynamic dictionary, they're not getting too out of date. They weren't computed using a radically kind of different version of the model. And importantly, you're not computing gradients on this momentum encoder. It's just a slow moving update of the query encoder. And they find that this can outperform ImageNet pre-trained counterpart in some detection and segmentation tasks. So it shows kind of promise as a self-supervised method for pre-training. Here's a comparison from the paper to the alternatives, which I feel is like quite helpful. And so what they call the end-to-end model, that's like SimCLR, where you have encoders on both sides. And this is very, very costly with large batches because first of all, you have to push the instance through this huge model, and then you have to propagate the gradients back again through this huge, deep model. And so it's just not realistic to have the batch sizes that you would need to get good negative examples. B is a memory bank. And there you just compute a static memory bank of encodings and you sample from that. And the reason why this is not as good is that some of the encodings could get quite out of date. And then finally is MoCo, which we just saw that uses this dynamic dictionary with a momentum encoder. And this is the performance. So on the x-axis, you see on a log scale the size of the kind of pseudo batch that the model effectively has access to. And, interestingly, they are running this on an 8 GPU machine with 32 gigabyte GPU card. So this is a machine that might put you back the better part of $500,000 just to buy. So it's not like they're running this on a puny computer, but they already run out of memory for the SimCLR style approach with batch size of 1024, whereas they can effectively access these much larger batch sizes by doing this dynamic dictionary lookup with the momentum encoder. And it's just in general doing better than the memory bank because the memory bank has some embeddings in there that are getting really outdated as the model is being updated during training. So the key takeaways, a way to make batch size effectively very large, so you don't need to worry about specifically mining hard negatives. And the representations are consistent as the model evolves during training. Interestingly, they find the model works better when they choose the momentum parameter of 0.999 versus 0.9, which comes back to this idea that the fact that the key representations are evolving kind of very slowly at each step means you can use this dynamic dictionary to get representations from past batches that are not too out of date. Because at each step, the model that you use to compute the new representations that are added to the dictionary has only changed a little bit from the previous model. There was a MoCo v2, and it added an MLP projection head like in SimCLR to make better behaved contrastive loss and stronger data augmentation, again, like in SimCLR. There's also something you might see called the XBM queue or cross-batch memory queue. So the basic intuition here is that embeddings drift at a slow enough rate throughout the training process that you can use the features of recent mini batches to directly connect each anchor in the current mini batch with embeddings from recent mini batches. So they argue that once the early stages of training are completed, the features are stable enough that you don't need this momentum update of a key encoder. You can just directly use encodings from the past mini batch. And so this is something to be aware of as well. In practice, you might not need this sort of strategy. It may work similarly well to mining hard negatives just once. And so you might initially train the model without hard negatives and then mine them once and use that as a sampling strategy for your next round of training. We found that worked pretty equivalent to the XBM queue. And so there's kind of different ways potentially to mine hard negatives, but in general they are important to the performance of contrastive learning, and if you just sample random negatives, that's unlikely to be sufficiently informative given that you're not able to run this over some kind of massive TPU. Okay, Another thing I'll quickly mention is deep cluster. So this is a bit of an older paper, but the idea of it is at each iteration you cluster data points using the prior representations and then produce the new cluster assignments as the classification targets for the new representations. And one of the things that's argued to be challenging about this is that it can be challenging to avoid a trivial solution. Okay. So in all of this with, the definition of contrastive learning, right, is that you want representations of the same instance to be, the instances from the same class to be similar and instances from different classes to be different. And you get that through this loss function where you compute the cosine similarity between the examples that are from the same class and divide that by the sum of the similarities of examples from different classes. And as I said, like at the heart of this literature is how you find informative enough negatives. And so there was this study in 2020 called Bootstrap Your Own Latent, which surprisingly was able to achieve state-of-the-art results without using negative samples at all. So let me explain what they're doing. So here they have an input image, X, and they take two data augmentations of that to get different views. So think of this maybe as two randomly cropped views of the same image. And then they pass those through encoders, which they use the term online encoder, represented by f of theta. So think of that like as a ResNet. And then they have this f of chi, which is the target encoder. And that creates representations y and y prime. And then they're going to project that, just like we saw previously, down into a lower dimension. Then they make a prediction, q theta of z, and they compare the representation from the online network to the target network. But importantly, there's this stop gradient on the target network. And so they're not going to update the target network through backprop. Instead, they're going to update the target network as a slow moving average of the online network. So this is a momentum encoder, like we saw with MoCo and like we saw with Dino. And so again, you have an online and a target network. And importantly, both of these have the same architecture. So they're both a ResNet. But again, only the online network is updated via gradient descent, whereas the target network is updated with a momentum encoder. And like SimCLR, they project the latent representations into lower dimensional vectors. And the loss is just the mean squared error between the L2 normalized prediction, q theta of z, and z prime that comes from the target encoder. And then they switch the two samples, and they compute this L tilde, and the final loss just adds them up. So here they put t through the online encoder and t prime through the target encoder, and they compute the loss, and then they flip it and put t prime through the online encoder and t through the target encoder, and again compute the loss, where the target encoder is a momentum encoder that's updated as a slow moving average of the online encoder. So it was suggested that that this works because it implicitly sees negative through batch norm. And it turns out batch norm isn't necessary, although it makes training and hyperparameter selection easier. Instead, there was a later paper by Chen and He, and again, like I think I mentioned in class, I think that Kai-Ming He just has this incredible intuition for what is happening when you try to minimize these massive functions and hundreds of millions of dimensions. And he had kind of a very informative paper on this as well. And they argue that Siamese representation learning can work without negative pairs, which is contrastive learning. It can work without large batch sizes, or even without a momentum encoder. What's necessary to prevent collapsing solutions is the stop gradient operation, which is implicit in a momentum encoder. And so by collapsing solutions, I mean what we talked about when we talked about Dino, how the model can learn just for every image that you put in it, it outputs a uniform vector, right? Or it outputs a vector that puts all the weight on a single value, and zero everything else. And so then that trivially like minimizes the loss, but you just get the exact same representation no matter what you put in it. And so like obviously that's useless. And so we want to avoid these collapsing solutions. And you don't need negative samples to avoid collapsing. You don't need large batch sizes. You don't need a momentum encoder, but you need the stop gradient operation. And kind of the intuition for that is that the target network here is updated as a very slow moving average of the online encoder. And so it just doesn't get to the collapse solution where they're both outputting, say, a uniform vector, because it's just updating kind of very, very slowly as the online encoder moves. And so it just doesn't have a chance to get to that collapse solution, and you can avoid the collapse solution that would cause problems with optimization. So in this paper by Chin and He, they say, really all you need is an architecture where on one side you have this encoder that you're updating, and on the other side you have a stop gradient operation, and then you can feed positive pairs into both sides of this, and you don't need negative, and you can avoid collapse. Although they do say that a momentum encoder gives you much better representation, so it's helpful to have a momentum encoder, but you don't have to have that to avoid collapse. You just cannot be updating the gradients on your encoder on the right. Okay, and there's this really great quote in the Chin and He paper that says, analogous to convolutions, which is a successful inductive bias via weight sharing for modeling translation invariance, the weight sharing Siamese networks can model invariance with respect to more complicated transformations, like data augmentations. We hope our exploration will motivate people to rethink the fundamental roles of Siamese architectures for unsupervised representation learning. And so what they're saying is, convolutions have been really powerful in computer vision and for tasks like object detection because they give us translation invariance. So as you move a dog around an image, because of the sliding window nature of convolutions, you can get the same an invariant representation for that dog. And essentially at its core, and we'll see this when we talk about applications, a lot of our applications come down to saying we want representations of things in the same class, regardless of like the noise that they might have, regardless of the intraclass variation, to have similar representations. And that's what a Siamese network does. And so you don't have to have the negative samples, but in practice, oftentimes they're useful. And like I was saying, like in a supervised setup, you might have an explicit way to mine really good hard negatives, or not to mine them, but to like select them ex ante. That's very useful for the model to learn from. And we'll see various examples of this when we get to applications. So by the way, if bootstrap your own latent sounds familiar, it's because it was the inspiration for Dino, which we talked about when we were talking about vision transformers. So Dino uses a different loss function and differs in some of the architectural details, but it essentially has like a similar intuition, so they were calling the online, the student, and the target, the teacher, but they also had this momentum encoder where it's like a slow moving average. And so it's essentially, it's different in some of the details, and they, like BYOL was in comparison and they beat it, but it's a very similar intuition. It's kind of this, I'd say, the more state-of-the-art version of this. All right, so that's self-supervised contrastive learning. As I said, we'll be talking a lot about supervised contrastive learning when we get to applications. So while contrastive learning took off in the self-supervised space, it soon became apparent that it can be very useful for supervised applications as well. And we'll see applications, for example, to OCR and record linkage later in the course. To just give a very famous example now that I think popularized contrastive learning in the supervised space is OpenAI's CLIP. So OpenAI are the people who brought you GPT and who have had other kind of very successful large models, CLIP being one of the foremost ones. And so CLIP is trained on image caption pairs. And so you have an image and then you have its caption, which is a text. And they train this contrastively. So for the M pairs in the batch, the model is trained to maximize the cosine similarity between the positive pairs, of which they're in, right? Because each image has a caption, and to minimize the cosine similarity for the n times n minus 1 incorrect pairs that are in batch using a symmetric cross entropy loss. CLIP is trained on 400 million image text caption pairs collected from the internet. So this is obviously a extremely large data set because they're OpenAI and that's what they do, is extremely large data sets. It transfers reasonably well to many other computer vision benchmark tasks. It does struggle with abstract tasks, such as counting the number of objects and with very fine-grained classification. It also does really bad on MNIST, which is digit recognition, so 0 to 9. And MNIST was like, you know, the application that neural networks did kind of like pretty well on back in the 1990s. And so it was kind of almost shockingly bad performance on MNIST for a model that's supposed to be getting us closer to like AGI. But they're very open about that. Like it's one of the examples that they give. And they say that when they went back and kind of like looked at and, you know, analyzed the images, there's almost no digits in the training sample. And so it's just out of distribution. And we'll talk more about CLIP when we get to multimodal learning in a couple of weeks. Okay, I want to say a word about semi-supervised learning now. So suppose you have a labeled data set that has positives in it, and then you have a large unlabeled data set. And so you could just do supervised learning on your labeled data. New classes can emerge in the test data that have never been seen in supervised training. And we might ask, is there any way to leverage the information in the unlabeled data to do better? Because we just saw an entire, literature on self-supervised training of vision encoders. So we have our supervised data set, which is great, but can we leverage our unlabeled information as well? This is a problem that's called open world semi-supervised learning, and I've cited a few papers here. I'm going to talk about the most recent one, which is a model called OpenCon. This is a 2023 paper, and so very new, and I think pretty exciting. And so let's say that you have some labeled data. So here you see you have some labels from ImageNet. You see that you have a couple of penguins, a couple of rabbits, and then you have a large unlabeled data set. And so first of all, it does what's called prototype-based learning. And so you take your data and you have these prototypes, which at the first step come from your labeled data, and you do clustering. And based on that, clustering, you can update the prototype. So here the blue and green are labeled data, and the stars are the prototypes, and those gray dots are unlabeled data. So they come from our big unlabeled data set. But based on the clustering, some of those gray dots, we think they're actually rabbits or penguins. And so they get clustered into the same group, and we update the prototype based on that. And then we have these points that are more than a threshold distance from the prototypes that have been computed so far. And those are labeled as novel classes. And again, you can do clustering and compute the prototypes for those novel classes. And so you see here, you have prototypes for known classes, which may be associated with unlabeled data points that we think, based on clustering, belong to the known class. And then you have these prototypes for novel classes. Okay, so with that done, how do you compute the loss? Well, you compute the standard SupCon loss for your labeled samples, just like you would do if you were only doing supervised contrastive learning. You compute SimCLR on the unlabeled samples using data augmentation, just like we saw in the previous section. And then you compute a third loss term using pseudo labels on the unlabeled data with SupCon. So this has a little bit of a similar flavor to the deep clustering we saw discussed above, but here you're computing SupCon over these pseudo clusters. And there was like a paper that preceded this that just did these first two things. And this paper found better results doing all three of these. So then the loss is just a weighted sum of these three terms. And these are two of kind of the earlier, by which I mean 2022, papers in this space. And they're doing visualization with UMAP and finding better representations from this approach. So as I said, this is a brand new paper, but I think it's potentially kind of an interesting area to think about how we combine our labeled data with a very kind of potentially very large unlabeled data set and try to get the best of both worlds by being able to get great model performance because we have these high quality labels, but also being able to squeeze as much as we can out of the unlabeled data. And so I think it'll be interesting to think about applying this to kind of various applications, which is something that in my group we're already doing. All right. And so now in the final part of the lecture, I want to say a word about contrastive learning in the language space. And again, we're going to see this more when we get to applications. So data augmentation is typically at the core of contrastive learning and vision applications. Obviously, it's what powers the model. If you're in a self-supervised setting, even in a supervised setting, you might also do data augmentations. The SupCon paper even includes it in its definition of the loss because it's just kind of assumed that you would do data augmentations. It's actually more difficult to do text augmentations that don't change the semantics of the text. So there's been different things that have been suggested, like lexical edits where you replace synonyms, random insertion, deletion, or swap. Back translation, where you translate into another language and then back, then use a framework like MoCo to contrastively train sentence embeddings. Or dropout, where you feed a sample into the encoder twice with different dropout masks, and these two versions are the positive pair, and then other embed samples are the negative pairs. So you might be asking now, kind of in the context of NLP, BERT has been pre-trained to give us semantically meaningful representations of tokens, or we can think of those as semantically meaningful representations of words and text. So say we want to do something like compute the semantic similarity. Are these two texts different ways of saying the same thing? You might think, why do we need a contrastive model to train sentence representations for semantic similarity? Hasn't kind of BERT already learned to do that, to give words similar representations based on their contexts? And it's been shown that the pre-trained sentence embeddings from BERT perform poorly off the shelf on semantic similarity tasks. In fact, in some applications, they do worse than average static GLOVE embeddings. And GLOVE is like a type of static word embedding, which are kind of a much, much older technology. To think about why this would be the case, remember that to measure similarity, we use simple metrics such as the dot product or the cosine similarity, whether it's a text or a vision representation. And so first we need to define some terms. So an embedding space is isotropic if the embeddings are uniformly distributed on each dimension, and it's anisotropic if the embeddings occupy a narrow cone in the vector space. And there's a number of papers that have pointed out that language models trained with a softmax law produce an anisotropic embedding space. And what's more, this is related to word frequency. So high frequency words concentrate densely and low frequency words concentrate sparsely further from the origin. And so when the contextual word representations are averaged to create a sentence representation, or, by sentence, I mean here, it could be literally a sentence, it could be a document representation. This sparsity can cause the sentence representation to locate in poorly defined areas, leading to poor performance. And so there's this method called BERT flow, where they try to transform the sentence embedding distribution into a smooth isotropic Gaussian distribution. The approach that has taken off even more is just to utilize the fact that we have good sources of supervised data for training sentence embeddings for semantic similarity tasks. So natural language inference data sets are the main source of supervised data for learning sentence embeddings. So does sentence A until sentence B contradict B, or is neutral with respect to B? And so the idea of sentence BERT is you encode these two texts using BERT, and then you have a pooling layer to get fixed size representations for the sentence. And again, sentence here is used liberally. It doesn't have to literally be a sentence. It can be any text that's up to the token limit. So like up to 512 tokens. They have a lot of different models that you can use. And then you compare the two embeddings with cosine similarity or with some other distance metric. And again, it could be SupCon, it could be triplet loss, etc. And so this gives an embedding per text, and that means each text only has to be embedded once, and the same embedding can be used to compare to any other text. And the vector space produced by SBERT can be seen as a metric space that has been explicitly trained to represent semantic similarity. You can apply standard clustering algorithms over the embeddings or dimensionality reduction algorithms for visualizations. And so in this architecture, it can be symmetric, where you fix the weights to be the same on both sides of the encoder, or it can be asymmetric, where it's both a BERT model, but you allow them to have different weights. And symmetric encoders tend to be used for applications where all texts are of the same type. So semantic textual similarity, duplicate detection, topic clustering, etc. Asymmetric encoders allow using different weights for different sides, and they're usually used when we have two different types of text, like question answering, maybe natural language inference, although in practice, it's argued that sometimes a symmetric encoder still gives better results. So the training data are pairs or groups of text with labels of the distance between them. And in SBERT, again, they have various models. So they have a version trained on cardinal continuous distances, on cardinal discrete distances, which is either they're the same or different, or an ordinal distances. B is closer to A than C is, which would be what you have for triplet loss. And SBERT is trained on various NLI data sets and on things like duplicate quora questions. So this is a question that's asking the same thing in different ways. And the really phenomenal thing about SBERT is they have an easy to use modular implementation with great documentation and lots of pre-trained models. So lots and lots of different language models trained on different data sets with different loss functions. So triplet loss versus SupCon versus contrastive loss, etc. And it's also highly optimized code. So, in the original paper, they tout how fast it is. And so it's just a really, really super useful resource for learning similar representations for sentences, which a lot of NLP tasks, you realize that they kind of boil down to that. And you can use their pre-trained model. It's not always exactly what we're after. So we experimented with our pre-trained expert representations, good, for representing topics in newspapers, and that was not really the case. Like sometimes they were, sometimes it was kind of weird, and of course they weren't trained to do that. They're trained on things like duplicate Quora questions and NLI. So off the shelf, it might not be exactly what you need for your application, and saying these things are the same and these things are different, but it makes a really great starting point. It's a really easy to use, optimized code base with lots of different options to mix and match different language models and different loss objectives. And so I would very highly recommend it if you're interested in working in the NLP space. And that's all I have on contrastive learning, and I will really look forward to talking more about this in class on Thursday. Thank you.